It is my pleasure to introduce Moisés Herradón Cueto. He's from Universidad Autónoma de Madrid, who will talk about Hodge theory of abelian covers of algebraic varieties. So, Moisés, thank you very much for accepting our invitation. And now you can start. Thank you.
Thank you. Thank you very much, Ellen, and all the organizers for having me here. It's an honor. I should start saying this is joint work with Valduque, Christian Geski, Laurencio Maxima, Moton Wang. So I'm going to talk about Alexander modules and Hodge structures. And so my plan is to define those things and then say some things we did. But I will start for a while by defining the words in my title. So Alexander modules are this topological invariant that has to do with covers. So as we know, covers have to do, covers are in bijection with subgroups of a fundamental group, and I care about covers that are regular and they have a deck group which is free abelian. So whenever you have an epimorphism to a deck group that is a 0 to the R, you got a cover. And Alexander modules, by definition, are the homology groups of these covers. And these are, in principle, they're vector spaces on over whatever field of coefficients you choose, but they're also modules because they have this deck transformation action. So if you just take some bijection between 0 to the R, or the generators of 0 to the R, and the R variables, you get an action of Laurent polynomial ring on homology. So these are Alexander modules. This is their module structure, and I want to study the Alexander modules of varieties, algebraic varieties. So the ones I want to look at, actually, they don't quite come from here. They come from algebra. They're going to come from maps to groups. So let me talk about that for a second. So this is going to be my setting for the whole talk. There's going to be a group which is abelian and algebraic. It's a semi-abelian variety. So you could think of C star. Really, you can just think of C star. That's an interesting enough example. You can think of a power of C star. You could think of an abelian variety, or in the most general setting, you could take an extension of one by the other, and then some smooth variety and an algebraic map. And from such a map, you get a cover in this way. The group has a cover. Its universal cover has abelian deck group because it's a group. I've written it as the tangent space. It's an affine space of the same dimension, and the covering map is the Lie group exponential. And if you have these two maps, you can construct a pullback, and you get this space U to the F, which, as the pullback, it lives inside a product, just the objects, the points in the product, such that f of x is x of z. So this shows that it's a complex manifold, and also, since you pull back a cover, pi, this new map you get here, pi is a cover. So you get a cover with the same deck group, and those are the covers that I want to look at. So I think very important question: am I studying the empty set? The answer is no. There are plenty of these, and the linear already answered this question, which is that actually I will talk about Hodge structures later, but whenever you have a Hodge structure map, since before I was talking about pi 1, but really since the groups are abelian, it will factor through H1. Whenever you have a mixed Hodge structure quotient, you get a corresponding, you get a G, a group variety, you get a map. And whatever mixed Hodge structures are, if you don't know the definition, doesn't matter really. I just want to point out whatever they are, the identity is a morphism of mixed Hodge structures. And this will give you the biggest possible cover with this deck group, free abelian deck group. So at least for any variety, the universal free abelian cover shows up this way, which is, it's nice. We're not studying the empty set. So with this in mind, we get Alexander modules. So if I just, so this diagram from the previous slide is going to be with us the whole time, where you have your F to a group, and you take a pullback and you get a cover, and the field of coefficients is going to be Q or R, doesn't matter almost. And we have the Laurent polynomial ring, which if I want to give it coordinates, I can, but I'm just thinking it's a group ring over the fundamental group of G. And like before, if I have this cover, the homology groups are going to be called the Alexander modules. So the first thing one can notice about these is that they are finitely generated modules. You can get here by using this theorem that says that U, being algebraic, has the homotopy type of a finite CW complex, and UF does not, but you can think of this homology as a local system on the space downstairs, a local system of R modules. When you take its homology, you get this same homology, and this will get you there. But it could be infinite dimensional for sure. So this is the reason why I'm going to talk about homology, even though in algebraic geometry it's much more common to talk about homology. It's just I'm a bit scared of what would happen if I looked at cohomology groups, because if you have an infinite dimensional group, for example, if you have a free module, it would be infinite dimensional, and the dual of an infinite dimensional thing is uncountably dimensional, and I don't want to deal with that. And I guess people generally don't want to talk about these modules either. There is such a thing as cohomology Alexander modules, but you would dualize over the ring instead of over the field. But anyway, for this reason, I'll talk about homology the whole time. So these are the objects of study. Let me tell you some, really the main example, the only example I keep in mind, which is what you get from hypersurfaces in affine space. This is already a very interesting example. So if we have a hypersurface cut out by some equations, R could be equal to 1, or maybe it's larger, and you look at the complement of the hypersurface, the equations give you maps to, in principle, to 3D but since you remove the zero sets, they actually land in C star. So this is my group now, and I get Alexander modules. And it's been known for a very, very long time that by looking at the complement, in particular looking at the Alexander modules, you can know stuff about the singularities of the hypersurface. And this is the most classical example. So maybe people have heard of it, but it's a really nice example. I just want to mention it. So if you have a curve of degree 6 with 6 cusps and transversal at infinity, then the complement is not always homeomorphic of all these possible the curves of this kind. And you can see that the first Alexander module is this space if the cusps are an conic, which since there are 6 of them, generic 5 would always lie in a conic, but 6 generically they wouldn't, and it vanishes otherwise. And with some work, this will tell you that the complements are not homeomorphic, which, well, it's a very old example, but still seems counterintuitive to me. It feels like you know what happens locally, how would line in a conic change the topology, but it does. One thing I should mention is that Zariski didn't use Alexander modules. He showed that the fundamental groups are different. They're not isomorphic. So, and I should say, the first Alexander module, it only depends on the fundamental group. So knowing the fundamental group is knowing strictly more. It's the Alexander module, the first one is strictly weaker than the fundamental group. So you lose some information by looking at Alexander modules, but you gain something, which is that fundamental groups finitely presented groups are complicated. If you give me 2 finitely presented groups, I will probably have no idea if they're isomorphic or not. But if you give me 2 vector spaces, I know that there are these 2. This one has dimension 2. This one has dimension 0. They are not they're different. So it's easier to deal with invariance, even though it's weaker, and it's still strong enough to know stuff, like to tell these examples apart, for example. And another motivation for Alexander modules is that if you think of a special case or a similar situation where you have a fibration, you get a very familiar thing. So I'm thinking now of letting the group be C star. So pi 1 would be Z. I'm thinking of the one variable case because in the Laurent polynomial has one variable in this case. A map to C star, it's generically a fibration, and in this case, it means that there's away from a finite set, it's nice. So there's a finite set of bad points, and you could take, for example, a ball around the origin and get rid of those bad points. And if you restrict, so you get, I'm thinking of the preimage as a tube around some sort of fiber at zero that I've removed here. You get a fibration. And you play the Alexander game over the ball. So you make the same diagram. So now we have a punctured ball, and I take the universal cover, which is a half plane, and this is the usual exponential e to the x. And I take the pullback. This is a cover with that group Z. This is a cover with that group Z. But now something more has happened because this was a fibration. So its pullback is a vibration over a half plane, which is contractible. So it's a globally trivial vibration. So up to homotopy, it's the fiber. Any inclusion of a fiber is a homotopy equivalence, and this means that the homology groups are the same. For example, the analogous thing to Alexander modules here are always finite dimensional, because F is an algebraic variety and it has finite dimensional homology groups. So if I took a global map to C star, then I probably wouldn't be a vibration. I wouldn't have this sort of thing. It wouldn't be finite dimensional. But one way to think about this is as a sort of analogous thing. And you could think of taking a homotopy, trying to work around the bad places and see that you get something related. Of course, then it won't be the same, but there's always a map, for example, between the generic fiber and the Alexander module, even though it doesn't have to be a homomorphism. And if you know about limit mixed-Hodge structures in this setting of the vibration, you will have the limit mixed-Hodge structure, and the Hodge structure I'm trying to talk about should be something analogous in this case. So the other objects of study are mixed-Hodge structures, and I will define them just to prove that they are a concrete thing, even though the concrete definition doesn't really matter to me. So there's pure Hodge structures and there's mixed Hodge structures, which are made of pure ones. So let me define the pure ones first. So I have a field which is Q or R, and a Hodge structure over this field is a vector space with some extra stuff, and it has a weight, which is an integer. And the extra stuff, like I'm saying, I don't care exactly what it is, but I want to show that it's concrete. So what it is a filtration on the complexification. So there's some complex vector spaces, one included in the previous one because it's decreasing, and it has to satisfy this property that when you take pieces and you conjugate them, you get a direct sum decomposition. So these two don't intersect. If you take when P plus Q equals n plus 1, if you take just one bigger, you can intersect them and maybe get something non-zero. And from here, you would get that this is a decomposition, which might be a definition you've seen. Often a Hodge structure is defined with a decomposition, but a filtration is the same thing because you can get the decomposition in this way. And if you had a decomposition, you would just add up the first, really the last few bits, and that would give you the filtration. It's just that the composition is nicer for me. So inclusion is just some vector space with some linear algebra information on it, and it's really not important what it is. But anyway, why would we care about this definition? The reason to care about is Hodge's theorem, which says that these show up in complex geometry. If you have an algebraic variety which is smooth and compact, he showed that you get a Hodge structure of weight m on the nth degree cohomology. And just by dualizing everything inside, you can define such a thing as a dual Hodge structure, which has negative weight, and homology would also have a Hodge structure. And this is very useful. Just knowing, there's a lot of conclusions you can get just from knowing that these exist. And of course, they have properties like functoriality. But for example, just by noticing that if the degree is odd, the composition will have no middle piece. So it will have to have even dimension. And this shows instantly that the odd degree, the cohomologies of varieties, which are smooth compact, are even dimensional. So if you construct a complex manifold with odd the dimensional H1, it cannot be a smooth compact variety. And this is a great source of examples. I mean, it's just the easiest thing you could, the easiest consequence you can get. So the reason to look at mixed Hodge structures is that so that you don't have to say smooth or compact here. And then you don't get Hodge structures, pure Hodge structures, you get mixed Hodge structures. So pretty much if you take Hodge structures of different weights and you add them all together as a direct sum, that's a mixed Hodge structure. Then the definition is slightly more general. They're not all direct sums, but I think that's a pretty good idea of what they are. And just to be very concrete, a mixed Hodge structure is just a space with some more linear algebra data in it. It has a filtration that we call the weight filtration on the space, and when you take the quotient of two pieces, you get a pure Hodge structure, and the degree of this filtration tells you the weight. And the pure Hodge structure comes from a Hodge filtration that has to exist on the original space, complexified. For example, you could take a direct sum of pure Hodge structures. So this is an even more long-winded definition. Again, it doesn't matter exactly what it says or what filtration is increasing or decreasing or what lives where, just that it's some definition. The actual important thing is that these show up in the cohomology of varieties that don't have to be smooth and don't have to be compact. So these are very useful for similar reasons to pure Hodge structures. That's why the Yin did this. For example, the first theorem I was talking about, telling you when you have maps to abelian algebraic groups, is a reason. Are there any questions, by the way? Well, I don't know. I'm not seeing faces, but like I said at the beginning, feel free to stop me at any point, or if someone writes something, hopefully, I'm very confident that Ellen will stop me if someone writes something.
Yeah, sure, Moisés. Thank you.
Thanks. So now that I have the definitions, this is the problem I want to talk about. Take the Alexander modules and put a Hodge structure in them, on them. So this is obviously impossible because just by a silly reason that mixed Hodge structures are by definition finite dimensional. These are infinite dimensional. So of course you could go around this and define the definitions I showed didn't require essentially finite dimensionality anywhere. but it's probably, I've never seen anyone study infinite dimensional Hodge structures like this. So it's probably not a very useful notion. And even if it was, I have no tools to work with infinite dimensional structures. So really, I need to look at something finite dimensional instead. The finiteness that we do have is over the ring. So what we're going to do is work around that using the module structure. And I can think of two ways, and I will talk about both. So one way, which makes a lot more sense in the one variable case, if the group is C star and the fundamental group is Z, the Laurent polynomial ring just has one variable, which makes it a principal ideal domain and means that every module is something torsion and something free. So what about throwing out the free parts and sticking with the torsion? You could do this always in more variables. You could always look at the biggest finite dimensional module, but it seems to make less and less sense if the number of variables gets bigger. And this smallest part does have, as you make it bigger, it does have a tendency to vanish often. So I don't want to make theorems about zero. So really, I think this makes the most sense in the one variable case. And instead of looking at submodules, a thing that captures a bit more information is to look at quotients. I don't know how to talk about any ideal, of course, but a very natural ideal to look at is set all the variables equal to 1. So for all the group generators, which are the variables that take for all the t's, t minus 1, and take that ideal. And you could take that ideal and you would get a quotient, or you could take bigger powers of that ideal and you would get larger and larger quotients. And that for any n, you take the nth power and you get a different quotient. And you could even ask for all of these to be compatible. It seems like a reasonable thing to ask. And I mean, both of these things ended up being the things we did. So let me talk about the first thing, which the 5 of us did, and then let me talk about the other case. So the first thing we did, this is the diagram from the beginning. There's a group, there's a universal cover, which is the exponential map, and the cover we get is cyclic, has that group Z. And on the torsion part of the Alexander module, we managed to show that there's a mixed Hodge structure. And we showed some things about it. One thing, so you could think of this theorem, so the cover is not algebraic. So you could think of this theorem as pushing the Lynch theory just a tiny bit into complex manifolds that are not algebraic. Or if you know what the limit mixed Hodge structure is, I think this is much more concrete, because it has a lot of properties that look just like the limit mixed Hodge structure. So I think it makes a lot of sense to think of this as some sort of global version, where the limit mixed Hodge structure would show up if you put a little ball instead of C in the place of C star, like I was doing earlier. So we proved a bunch of properties of this mixed Hodge structure, and I will show my favorite corollary because, I like, and the reason I like it is that it's a theorem that makes no mention of Hodge structures, but we don't know. I don't know how to prove it without them. So the thing is, just having it enables you to show a lot of stuff. So the torsion part is a finite dimensional vector space. T, the variable in the ring, is acting on it. So I can think of a matrix, and it can think of its Jordan normal form, and it will have blocks. And we can show that the blocks we can bound them by this weird-looking function. But if you think about it, it's a triangle. In the middle dimension, it gets bigger, and then it has slope 1/2. I don't know what to say about this formula, except when j equals 1, you get 1. So you get Jordan blocks of size 1. So you get a diagonalizable matrix. And this for me opens up a lot of questions, because makes me wonder about the semi-simplicity of Alexander modules. And it's a topic that I have no idea about. So if you look to the literature, the examples I know from the literature, they are all, as far as I know, semi-simple, but also the vast majority of them are the first one, which is a lot easier to compute, because you can get it from the fundamental group. So in short, to summarize, I have no idea if Alexander modules are semi-simple, and I would love to know. There are some examples. Liv Gober gave an example real quickly after we asked. But his example does not come from algebra. So there's a variety where there's a cover, but it does not come from a matrix star. But it's true that it doesn't have to be semi-simple in that case. And then our group, we found an example, but again, it's not very satisfying because the variety is not smooth. And I would like to know, and well, even those are both for H1, which in the smooth case we know cannot, has to be semi-simple. But in general, I have no idea if Alexander modules of hypersurface complements are semi-simple, or even hyperplane complements, hyperplane arrangement complements. I would love to know. Maybe they are. I don't know. This is a question I'm really interested about, and this slide contains all my knowledge about it. But I'm very interested if I can ever find someone who gives me answers. I would like to say something more about this Hodge structure, which is a relation that it has with other things which are well known and well loved, which is the Milnor fiber in the case of a global fibration. So when you have a weighted homogeneous polynomial, all the fibers are the same, they are diffeomorphic, and any fiber you could say is the global Milnor fiber. So then it's the same situation that I had before. Before I had it locally over a ball, I had a fibration, and the cyclic cover became up to homotopy just the fiber. And this is the same situation for the same reason. It has a fibration which is trivial over C. So in this case, the cover is the fiber, and their homology groups are the same. And you put, and also the fiber is an algebraic variety, so it has a mixed structure given to it by the linear, and we gave a mixed structure to the covering, and we gave them the same mixed structure, which is very comforting to know that we didn't. It's a very nice sanity check that disagrees with the things that everybody understands to be correct definitions. We define a thing that agrees with what sane people think should be defined. So let me now talk about how we generalize this with Valduca to any group and any variety and more variables. So this is what I was hinting at before, that in the case I was before, any cover coming from a map to a group gets a Hodge structure. Oh, I wrote Q. I don't know this over Q. I know this over R. Sorry. All these quotients by the augmentation ideal and its powers, they all get Hodge structures. They all agree, and you could even just by some tautological definition say that the inverse limit has some sort of inverse limit of Hodge structures, which is, well, it's not adding any new information. And for example, we showed these are in principle two different definitions, but we showed since the torsion, part of the torsion would live inside here, the mix of structures we showed do agree. And so the construction is, I think, fairly ugly and involved. There's a lot of the RAM complexes and sheaves, and if I wouldn't know how to compute anything with it. But I also think if you gave me the definition of, for example, singular homology, I don't know how to compute anything with that definition either. So the hope that I would have is to, with homology, you prove a lot of theorems, and in the end, with those theorems, you get to compute stuff. I would like to prove enough theorems about this Hodge structure that would allow me to compute it in a lot of cases. So, for example, homology has functoriality. You have a map of varieties. It gives you a map of homology groups. And we have a similar thing here. So, but here I have two things. I have U and G, and I could change either. So let me talk about what happens if I change one or the other. So say I stick with the same group, and I take a map of varieties. And each group maps to, each variety maps to the group by these maps of 1 F2. And say, of course, assume that the map between varieties is compatible. Then for each of these Fs, you get an abelian cover. And now by abstract nonsense, by the universal property of this fiber products, you will get a map between covers. So you could ask questions about this map of covers. And on the other side, you could change the group and leave the variety fixed. So say I have U fixed, and now I have a group homomorphism. And really the interesting case is where you say that all the maps in fundamental groups involved are epimorphisms, because if you don't have an epimorphism, the covers become disconnected. You get copies of the same thing, so that's not very exciting. These things are direct sums. But if you have epimorphisms, you're looking at the kernels, and one quotient will be a quotient of the other. And the correspondence between subgroups of pi 1 and coverings will tell you that the larger quotient gives you a cover of the smaller quotient's cover. So you get a tower of coverings. Or you could think of the correspondence goes by taking the universal cover, quotienting by H1, you get UH1, quotienting by H2, you get UH2. So either way, whenever you have G1 mapping to G2, you get corresponding map of covers. And you could just put both of these together into a picture where you change the variety and the group at the same time, like in this diagram that I'm about to draw. So say we have two groups, two varieties, one map between the groups, between either group and its corresponding, either variety and its corresponding group, and some maps connecting them. So you construct for each of the groups their universal covering spaces, which you can think of as the tangent spaces at the identity. So this lifts uniquely to a map which is the differential at the origin. These are affine spaces, and this is a linear map. And for each of these covers that you have, you can pull them back to get a cover of each of your varieties with whatever the group gives you. And now, because of, again, the property of fiber products, you get a map relating the covers. So this map gives you a map in homology, and for every quotient, you get a mixed Hodge structure morphism. And this we managed to prove. So this is, I don't know, this is very general. I feel like I haven't even thought of all the things you could do with this. Let me show you just one very, very particular example, which gives you a very nice corollary. So you have, there's 4 things here and a lot of maps to change around. So I'm just going to take G2 and make it the trivial group, and take both varieties and make them the same, make them map the identity. So if you have, so this is the same diagram. The second group is trivial, it's a point. The second variety is the same as the first. And of course, the universal cover of a point is a point. you lift that, you get the identity map, and the map between coverings is the covering map, because you try to you're pulling back the identity. So the map that appears here, what was called G tilde before, is now the original covering map. And what you get as a corollary is that the covering map gives you a morphism of mixed structures. And here you should say you put our mixed structure, but if you look at our construction, it's clear that it's the same as the one that everyone likes. So this is, again, very nice sanity check. We constructed something, we didn't go insane. We constructed a thing that matches the lineage mixed structure. And if we didn't do that, we should probably get worried. So, and from here, you can get a lot of corollaries, like the one with the Milnor fiber I was talking about is really a consequence of this theorem. Let me show one other property, and then just one other property, which is what happens with the module structure. So what happens with the module structure? Okay, this is what happens. And there's something that might be very strange depending on your background. Really, I'm saying that multiplication is a morphism of Hodge structures, which is what you would expect. But there's a logarithm here. So what I mean by the logarithm, first of all, is that I have an element. I think these are in the wrong order. No, sorry. Gamma is in H1 of G, but I'm thinking it's a matrix, and a power of it minus 1 to the n is 0. So it's a unipotent matrix. It's a matrix with ones. The only eigenvalue is 1. So that's a logarithm which is nilpotent. Or just take so this is what I mean by the logarithm, or this Taylor series, the log of 1 plus x evaluated at x equals gamma minus 1. So this seems very strange, but it's not. If you know the limit mixed structure, then you know that the exact same thing happens with the limit mixed structure. So I guess for if you're coming from Hodge theory, this seems very sensical. But I don't know. So I guess to me it seems strange. I don't know that much Hodge theory. I don't have an intuitive reason why this should work. It's just that in general, logarithms seem to appear in these kind of constructions. And then there's this fact that I'm writing a tensor product. This is just because I guess I couldn't say just a single gamma gives you a Hodge structure morphism. That wouldn't be true because of how it's defined. But really what I'm saying is that the degree is add in the way you would expect. If you unravel this definition, I'm saying, of course, the map is defined over Q. And then if you have something with Hodge degree 1, it will add 1 to the Hodge degrees. And if you had weight 2, it will add 2 to the Hodge weights. So this logarithm is a bit strange, but this is the best thing you would expect. So this should also give you some tools to compute stuff about the Hodge structure, because if you know some of these numbers and you know the action, you can get the numbers for other elements. And lastly, let me talk about ideals that are not the augmentation ideal. So it turns out that you don't have to do extra work to get larger quotients of the Alexander module, with what we already have. So the trick is that you change your setting, you change the variety, and you use this theorem that I was talking about before, and you get larger quotients for free. So what you do is you take a finite cover of a group, and if you pull back this finite cover, you will get a finite cover of your variety, which is again a smooth variety itself, and there will be a map. And this is again the same sort of setting where you have a group, a variety, and a map between them. So this finite cover of the group lies between it and its universal cover. So for the same reason, this cover lies between it and the cover I would get, which I'm calling UF. So if you construct the universal abelian cover of Gn, you get the same thing as for G. You get the same thing, you get the same cover. But the thing is that group is smaller, because when you quotient by it, you get a larger thing. So you're getting the same thing with a smaller group acting on it, or a smaller ring if you think of the group ring. And the fact you're looking at the same homology groups, but now the quotient, the ideal that I'm putting in the denominator, is smaller, because these gammas live in a smaller subgroup, whichever group I chose in the very beginning. And the theorem from before with the big cube diagram said that automatically you know that this is a mixed structure morphism. So you got to quotient by a smaller ideal. Really, for example, you could say that the generators, instead of saying that there are one, you could say that an nth power. You could take the group generated by nth power of nth powers of any generator, and then you will get an ideal that, instead of looking at the points 1, 1, 1, 1, 1, looks at every nth root of unity. I don't know how to look at any other ideals that are not really living on torsion points of the spec of the Laurent polynomial ring, but this we can do, and I have no idea if I don't know if I believe it's possible to do this for other points, not with our tools really. So this is what I was saying. I just copied the same diagram. You have your Alexander module, but it's quotiented by a smaller ideal. And if you take a group, I guess this n tilde would be this other n to the rth power, but I don't really care. And say you take powers of each generator. So then what I'm saying is the generators here are the nth powers of the variables. And I'm looking at this quotient. And so now I have matrices, but instead of being unipotent, an nth power of them is unipotent. So one thing we could do is take the Jordan forms of all of them and split the space according to which eigenvalue you get for which. At least for over the complex numbers, you could do this. So for every set of roots of unity, you would get a direct sum decomposition. And keep in mind, these all commute with each other. So the last theorem I'm going to show is that this decomposition is actually a decomposition of Hodge structures, with a small asterisk that, of course, this only works over the complex numbers. If you wanted to do it to make a statement over the reals, you would have to take conjugate pairs of roots and put them together. And if you wanted to talk about the rational numbers, you would take Galois conjugate sets and put them together. So really, you could say, instead of saying Galois orbits, look at the minimal polynomial, which is what I'm saying here. And for any polynomial, you have, you could talk about a Hodge structure, define over the correct field, and this is the mixed Hodge structure. So you get all your torsion points, and in the most reasonable way, that gives you a direct sum decomposition of Hodge structures, which is also something that happens for the limit mixed Hodge structure. So I guess this would be an expected thing to happen. So it's nice that it does. Okay, that's all I have. Thank you very much.